The human brain remains one of science's greatest mysteries. While we have mastered the art of creating computers by arranging transistors into logical circuits, understanding how neurons compute is a lot more challenging. After all, we did not engineer them ourselves. In an attempt to unravel this, scientists have created mathematical models, simplified descriptions that capture the essence of how neurons work. In this video, we will explore the Hodgkin-Huxley model, a Nobel Prize-winning breakthrough that many consider to be the most important equation in computational neuroscience. In their pioneering work, Alan Hodgkin and Andrew Huxley gave the first mathematical description of how neurons generate and propagate electrical signals. In fact, these equations are so fundamental that I have them tattooed on my forearm. In this video, we will build an intuitive understanding of the biophysics behind neuronal computations from the ground up. Our primary tools will be derivatives and differential equations that we covered in the previous video in the series. Today, we will take the framework of dynamical systems and apply it to neurons to describe how cells change their states over time, enabling such a rich variety of computations. If you're interested, stay tuned. To begin describing a neuron's behavior, we need to clarify what exactly we want to model. A living cell is an incredibly complex system, so we will have to make significant simplifications. Using the terminology from the previous video, we need to pick state variables. Let's start with the most crucial one, the membrane voltage. Imagine a neuron as a tiny bag filled with water and various dissolved particles, floating in a sea of similar fluid. The thin barrier separating these two environments, called the cell membrane, is where all the action happens. The particles dissolved in the water both inside and outside the cell are called ions, and they carry electric charge. Some are positive and some are negative. Now here's the key fact. The composition of ions on both sides of the membrane is different. Crucially for our discussion, the inside of the cell contains more negative charge than the outside. This separation of charges creates what is known as electrical potential or voltage. You can think of voltage as a measure of potential energy, arising from the imbalance of charges across the membrane. It is similar to the potential energy of water held behind a dam. Just as water has the potential to flow downhill and do work, the separated charges have the potential to flow and create the electrical current, if given a path to do so. If the membrane were freely permeable to ions, this energy would get converted into the kinetic energy of ions flowing through the barrier, dissipating the charge imbalance. However, when the membrane is impermeable, excess charge has nowhere to flow, and this potential energy remains stored. The amount of energy stored depends on both the magnitude of the charge difference and the physical properties of the membrane, such as its thickness and area. This ability to store electric charge is called capacitance. The behavior of a capacitor is described by a fundamental equation that relates the stored charge to the voltage across the membrane. To understand neuronal dynamics, we need to consider how this equation changes over time. Taking the time derivative, or the rate of change of both sides, gives us the following equation. It describes how the voltage changes as charges redistribute across the membrane. However, real neurons are more complex than perfect capacitors. The membrane isn't completely impermeable. It has specialized protein channels that open and close, allowing specific ions to flow across the membrane. These pathways for ion flow can be thought of as resistors working alongside our capacitor. When ions physically cross the membrane through these pathways, they create electrical currents that alter the distribution of charge. Since current is defined as the rate of change of the electric charge, we can rewrite our final equation in the following way, where the right-hand side represents the sum of all ionic currents flowing through the membrane. This equation marks our first crucial step in understanding neuronal dynamics. It links the rate of change of membrane voltage to the various currents flowing across the membrane. Before we talk about the underlying differential equations, Let's get a rough sketch of what's going on when a neuron fires. There are two types of ions that play the crucial role and whose dynamics we will describe: sodium and potassium. Think of an action potential as a brief electrical pulse caused by a precisely coordinated way of how these ions flow through channels in the membrane. It starts when the membrane voltage rises slightly above its resting level, crossing a certain threshold. This depolarization causes sodium channels to begin opening, allowing sodium ions, which carry positive charge, to flow into the cell, and thus cause even more depolarization. After a brief period of opening, sodium channels close, blocking the influx of positive charge. At the same time, channels of another kind open, allowing positively charged potassium ions to leave the cell, driving the membrane voltage back down to its resting level. The entire sequence takes just a few milliseconds, but it's the fundamental signal that neurons use to transmit information. This conceptual description makes intuitive sense, but it's unclear how do channels coordinate to ensure that they're opening in a proper sequence. After all, there is no doorman that would open and close channels when required. So how is this dance orchestrated biophysically? We'll begin by discussing what exactly makes ions move across the membrane. The rate at which ions flow through the channels depends on two key factors: how many channels are open and how strong the driving force is. There are two physical processes that determine this driving force. First, there is diffusion, the tendency of particles to spread from areas of high concentration to low concentration. You can think of it as a purely statistical process. If you have more particles on one side, by random motion, they are more likely to bump into channels from that side and pass through. This is the same reason why a drop of food coloring spreads through water. Second, there is the electrical force. Since ions carry charge, they are attracted to opposite charges and repelled by like charges. Remember that in the intact physiological condition, there is an excess of negative charge inside the neuron. This means positive ions are attracted inward, while negative ions are pushed outward. Now, here's where it gets interesting. These two forces often oppose each other. Let's take potassium as an example. There are more potassium ions inside the cell than outside, so diffusion tries to push them out. But since potassium is positively charged, it is electrically attracted to flow into the cell to neutralize the excess negative charge. Which force wins depends on both the concentration ratio of ions and the membrane voltage. For any given concentration ratio, there exists a special value of membrane voltage, known as the equilibrium potential, where the electrical force exactly balances the diffusion force. At this voltage, even though individual ions are still moving back and forth through open channels, there is no net flow. For every ion that moves in one direction, another one moves in the opposite direction. When the membrane voltage differs from this equilibrium potential, there is a net flow of ions that tends to drive the membrane potential towards the equilibrium. Let's make this more concrete with an example. In a typical neuron, there are about 30 times as many potassium ions inside the cell as outside, creating a strong outward diffusive force. The corresponding equilibrium potential is about -90 millivolts. If the membrane potential is less negative, let's say -50 millivolts, the electrical force is too weak and the diffusion dominates, causing potassium to flow outwards. This removes positive charge from the cell, making the membrane potential more negative until it reaches -90. Conversely, if the membrane voltage is more negative than the equilibrium potential, let's say -120 millivolts, the electrical attraction becomes so strong that it causes a net influx of potassium ions, reducing the excess negative charge until the membrane voltage settles back around -90. We can express this mathematically. For each ion, the current flow through open channels is proportional to the difference between the actual membrane voltage and the equilibrium potential. This difference is what we call the driving force. The proportionality constant is called conductance. which represents how many channels are open and how easily ions flow through them. If you remember Ohm's law from physics, this is exactly that, with conductance being the inverse of resistance. So far we have treated the conductance as a fixed property of the membrane, as if ion channels were simply holes that were permanently open. But real neurons are far more interesting. Many of the ion channels are voltage dependent, meaning that they open and close depending on the membrane voltage itself. Thus, our quest until the end of the video would be to arrive at the expression for G as a function of voltage, completing our description. Despite the drastically different roles of sodium and potassium in generating the action potential, the underlying formalism for describing voltage-dependent conductance is basically the same for different ions, apart from a few technical details. Let's first express the conductance to be the product of two factors. Here, G bar represents the maximum conductance hypothetically possible if all of the ion channels were open. This is a constant determined by the total number of channels present in the membrane and the conductance of each channel when it's open. Thus, it does not change with time. The second factor, P, is a number between 0 and 1, representing the fraction of ion channels that are open at any given time, which depends on the membrane voltage. The fraction of open channels is basically the same thing as the probability that a channel is found in an open state. How can we think about this probability of a channel being open? For that, let's zoom even closer. Each ion channel is a complex protein machine that changes its shape in response to membrane voltage, either allowing or blocking ion flow. There are various molecular mechanisms of how that might happen, and the details are not fully resolved. But broadly, channel proteins have charged parts, let's call them gates, that move in response to the electrical field across the membrane. Each such gate can exist in one of two positions, permissive and non-permissive. Whether the channel as a whole allows ions to flow depends on whether all the gates inside it are in the correct permissive states. Kind of how inside a lock, multiple pins need to be in the correct position for the door to open. Let's call the probability of finding a given gate in its permissive position as n. We are looking to arrive at a differential equation for n. How fast does the number of permissive gates change? Well, let's think about it in terms of transitions between the states. Since there are only two possible configurations, n can increase if a gate that was in a non-permissive position moves. There are 1 minus n gates that are non-permissive, and let's say they are opening with a certain rate alpha. Alternatively, n can decrease if one of the gates that is currently in the permissive position changes its state to non-permissive. By definition, at a given moment, there are n permissive gates, and we can denote the rate of closing as beta. This results in the following differential equation, where both opening and closing rates depend on voltage. In their original work, Hodgkin and Huxley determined the equation for alpha and beta empirically through careful experimental measurements. The voltage dependence of these rate factors reflects a complex physical process of charged amino acid residues moving within the membrane under the influence of electric field. While there isn't any elegant closed-form expression that can be intuitively derived to describe this, Hodgkin and Huxley found that certain mathematical forms involving combination of linear terms and exponentials could fit their data remarkably well. With these empirical expressions for alpha and beta as functions of voltage, we can numerically solve the differential equation that governs the fraction of individual gates in the permissive state. But what about channels that require multiple gates to be in the correct configuration to allow ion flow? Here, the probability theory gives us a simple answer. If the probability of a single gate being in its permissive state is n, then for a channel with 4 independent gates, for example, the probability of all gates being permissive, and thus the channel being open, must be n raised to the 4th power. This is precisely what Hodgkin and Huxley found for potassium currents. the conductance was proportional to the fourth power of n. What makes this finding truly remarkable is that at the time of these experiments, the molecular structure of potassium channels was completely unknown. The fourth power emerged purely from fitting curves to their experimental data. Decades later, when researchers could finally examine channel structures using X-ray crystallography, they confirmed that each potassium channel indeed contains 4 identical subunits that work together to control ion flow. So far, we have a description of a cell that only contains voltage-gated potassium channels, with the following 2 differential equations. One expressing changes in the membrane voltage as a function of potassium current, and one for potassium conductance as a function of membrane voltage. But potassium alone is not enough to make neuron generate an action potential. The formalism for describing sodium currents is exactly the same, but instead of 4 identical gates, each sodium channel has gates of 2 different kinds, with the conductance following a different pattern. Here, M represents one type of gate, analogous to N for potassium channels, but we need 3 of them, hence the cubic power. There is also an additional factor H, representing a completely different type of gate, with its own distinct properties. While the M gates open in response to increased voltage, making the channel more likely to conduct, the H gate does the opposite. It closes with sustained depolarization, in a process known as inactivation. But the differential equations for M and H have similar flavor to potassium gates, just with different constants in the alpha and beta functions. This concludes our description of voltage-dependent ionic conductance. Now, I realize that this is a lot of information, so let's step back and review the journey that we've taken. We started with a fundamental question: how can we describe the neuron's electrical behavior mathematically? Our first key insight was that the most important variable to keep track of is membrane voltage, the difference in electrical potential between inside and outside the cell. This voltage arises due to the charge separation across the cell membrane, which acts as a leaky capacitor, storing electrical energy. This led us to the first equation, relating the rate of change of membrane voltage to various currents flowing across the membrane. To understand these currents, we found that the behavior of each ion follows a similar pattern given by Ohm's law. Here, E is the equilibrium potential, determined by the concentration ratios of a given ion on both sides of the membrane. The real complexity and the beauty of the model lies in how these conductances depend on voltage. Hodgkin and Huxley experimentally discovered that we need 2 types of ionic currents to explain the neuronal dynamics. A potassium current with conductance proportional to n to the 4th, where n represents a probability of a single gate being in the permissive position, and a sodium current with conductance proportional to m cubed times h, where m and h represent 2 different types of gates. Each of the 3 gating variables follows its own differential equation in this form, where x represents any of these variables, and alpha and beta are voltage-dependent rate constants determined experimentally. To allow for more realistic dynamics, we often include a small leak current into the equation for voltage, which corresponds to various ions moving through the channels that are permanently open and thus have a constant conductance. There is one more important point to clarify. Everything we have discussed so far treats the neuron as a single point, assuming the membrane voltage is the same everywhere in the cell. This approximation works well for small neurons, or when we are primarily interested in what happens near the cell body. However, real neurons have complex branching structures, dendrites that receive inputs, and axons that transmit signals, and the membrane voltage can vary significantly across these different locations. To handle this spatial complexity, we essentially divide the neuron into many small segments and apply the Hodgkin-Huxley equations to each segment, adding terms that describe how current flows between neighboring segments. This gives us a system of coupled differential equations where each segment's voltage depends on both its local ion channels and on current flows from neighbors. The result in mathematics becomes more complex, but the core principles remain the same. Everything is still governed by ions flowing through voltage-dependent channels, just with the added consideration of how these currents spread through the neuron's elaborate morphology. What we talked about today is the most complete mathematical description of how neurons generate electrical signals, capturing the intricate dance of ion channels with remarkable accuracy. However, this completeness comes at a cost. Our model consists of 4 coupled differential equations, 1 for voltage and 3 for different gating variables. While we can easily solve those equations numerically and simulate a neuron on a computer, the high dimensionality makes it very difficult to gain intuitive understanding. With 4 equations, we cannot directly visualize the system's state in the phase space, a powerful geometric tool that would allow us to see how neurons transition between resting and firing states. In the following video, we will see how we can strategically simplify the full Hodgkin-Huxley model to just 2 variables while preserving the essential features. This reduction will allow us to directly visualize systems dynamics in a 2-dimensional phase plane, revealing beautiful geometric insights into neuronal excitability. We will explore why exactly neurons behave the way they do, and how subtle changes in parameters can lead to dramatically different patterns of electrical activity. In the meantime, if you're interested to dive even deeper into the fundamentals of neural computation, our today's sponsor has exactly what you need. Brilliant.org is an innovative online platform offering engaging courses across STEM fields. What sets Brilliant apart is their unique focus on hands-on learning. Rather than just reading textbooks, you'll develop intuitive understanding and problem-solving skills through bite-sized, interactive lessons. 2 courses primarily relevant to today's topic are electricity and magnetism and classical mechanics. The first one covers the foundational physics of charged particles, exploring concepts like Coulomb's law and electric fields, essential principles behind neural dynamics. The classical mechanics course complements this perfectly, helping you master crucial concepts like forces, work, and forms of energy. Brilliant also offers an extensive collection of courses in math, programming, and related fields. Whether you're just starting out and want to build a strong foundation, or if you're looking to expand your knowledge into new domains, Brilliant is an invaluable resource. If you're ready to embrace your curiosity, head to brilliant.org/Artem to get a 30-day free trial of everything Brilliant has to offer, plus a 20% discount on annual subscription. If you enjoyed the video, share it with your friends, subscribe to the channel if you haven't already, and press the like button. Also, consider supporting me on Patreon, where you can vote for video topics and get access to bonus content, like the written versions of the video scripts containing math details. Stay tuned for more interesting topics coming up. Goodbye, and thank you for the interest in the brain.